Hi everyone, welcome to Practical Electronics. We are now done with the fundamentals portion of these tutorials. We now get to look at semiconductors. For this tutorial, we're going to look at diodes and diode circuits. The components we've looked at so far are known as linear components. Semiconductors are conductors whose properties may be changed by external factors such as voltage or current. They allow or resist the flow of current based on these external factors. Semiconductors allow for some intelligence to be applied in electronics. Diodes are the simplest form of semiconductors. In this tutorial, we'll look at how diodes work and explore their use cases through a number of circuits. Let's look at the lesson plan. We'll do a recap on the basic functions of a diode. Then we'll expand on some of those characteristics. Then we'll take some time to explore use cases for diodes. And then we conclude by looking at some further material for learning. Let's look at some theory. Diodes are semiconductor components. They are passive but non-linear. They allow the flow of current only in one direction. This is a key characteristic of diodes. The arrow on the symbol points in the direction of the forward current. The symbol can be seen on the bottom right of the screen for a normal diode and a Zener diode. They do not have any resistance, and as such they don't follow Ohm's law. The typical voltage drop of a diode is between 0.5 to 0.8 volts. A Zener diode is a special kind of diode that allows the flow of reverse current when a specific voltage is reached. This voltage is known as a breakdown voltage. Diodes are very useful in electronics, therefore they have many use cases. We use them for rectification or power supply filtering, split voltage supply, voltage multipliers, regulation, using them as clamps and limiters. We also use them for protection as clamps and limiters, and we also use them as logic gates. These are photos of some diodes. Other types of diodes are LEDs, fully known as light emitting diodes. Let's look at our circuits now. The first circuit is that of a half-wave rectifier. A half-wave rectifier will take a sinusoidal input, meaning an AC input voltage, and the output will be clipped because the diode only allows current to flow in one direction. So when it flows positively, the output will match, it will also be positive. Then you will get no output for the negative part of the cycle. A full wave rectifier allows us to rectify for the full cycle. This we have done before when we were looking at our first power supply. Full wave rectifiers are very common, and some do come pre-packaged as well. A voltage clipper follows the same principle of diodes allowing current to only flow in one direction. For you to have a full wave voltage clipper, you need to place two diodes in opposite directions. For this to work, you need a reference voltage for your diodes. The voltage reference is applied to a variable resistor to allow you to adjust the point of clipping. For an input such as this, which is an AC input, you will get an output that looks like this, where the voltage is clipped at a maximum and clipped also at a minimum. Right, and on the screen now we have a voltage doubler circuit. This will double the voltage at the input, giving us a voltage at the output with twice the magnitude of the input voltage. During the negative half of the input cycle, diode 2 is forward biased. It conducts to charge the pump capacitor, which is C1. to the peak value of the input voltage. Because there's no return path for the capacitor to discharge into, it remains fully charged, acting as a storage device in series with the voltage supply. At the same time, D1 conducts via D2, charging up capacitor C2. During the positive half cycle, D2 is reverse biased, blocking the discharging of C1, while D1 is forward biased, charging up capacitor C2. But because there's a voltage across capacitor C1 already equal to the peak input voltage, C2 charges to twice the peak voltage of the input signal, giving us a voltage doubler effect. Right, and now we're looking at a voltage regulator. For this, we need to use a Zener diode. Zener diodes allow current to flow in the opposite direction only when certain voltage are reached. So for this specific application, there will be a fixed voltage across the Zener diode. The rest of the voltage will be consumed over the resistor. Zener diodes can also be used for protection to limit their voltage at any point in the circuit. Let's take a look at the logic gates. For us to understand logic gates, we have to go into the realm of digital electronics. So far, we've been looking at analog electronics in our tutorials. In analog electronics, signals can have multiple continuous values. In digital electronics, however, a signal is either on or off. The state of a signal being on and off is popularly represented with ones and zeros. Digital signals offer the advantage of being transmissible over large distances without loss of signal due to voltage drop. Logic gates are used to make simple decisions based on input signals. A gate monitors input signals and produces an output signal based on the signals received. On the screen, we have what's known as an AND gate. An AND gate produces a positive output only when both inputs are positive. So the signal applied to D1 and to D2 have to be positive in order for the LED to turn on. On the right side of the screen, there's a logic table showing us the output for each of the inputs. When both inputs are 0, the output will be 0. When one of the inputs is 0, the output will be 0. Only when both inputs are 1, the output will be 1. Meaning that the LED will only turn on if the positive voltage is applied to each of the inputs. Next, we have an OR gate. An OR gate produces a positive output when either one of the inputs are positive. When both inputs are 0, the LED will be off. When one of the inputs is 1, the LED will be on. And when both inputs are 1, the LED will also be on. The opposite of an OR gate is known as a NOR gate. A NOR gate will produce a positive output only if neither one of the inputs is positive. When both inputs are 0, the LED will be on. When one of the inputs is 1 or 0, the LED will be off. And when both inputs are at 1, the LED will be off. Let's take some time to build some of these circuits. We're going to build 3 circuits for us to properly understand the characteristics of diodes. And these can be seen on the screen. Here we have our first circuit, which is a simple LED circuit with a diode in series that's forward biased. When the current flows in the positive direction, the LED will turn on. But because the LED itself is also a diode, if we switch the polarity, meaning that if we switch the terminals around, it will not go on. The diode would not turn on. When we switch it back around, it will turn on once again. Similarly, if we switch the diode around, the LED will not turn on. And when we switch it back, the LED will turn on. The second circuit we're going to build is an AND gate. If you remember, for this circuit to work, for the LED to turn on, both inputs have to be positive. So we're going to use the orange wire to apply an input to terminal A, and then we're going to use a green wire to apply an input to terminal B. When both inputs are negative, we will not get an LED output. When either one of the inputs is negative, the LED will not turn on. Only when both inputs are positive will we get the LED to turn on. The third circuit we're going to build is a voltage regulator using a Zener diode. And this is how it looks. Right. If you remember, with a Zener diode, it's going to allow current to flow in the opposite direction only if a certain voltage is reached. So for this specific Zener diode, the reverse breakdown voltage is 5.1 volts. We are going to use a multimeter to measure the voltage across the diode. With the first measurement, something seems to be out of place. This voltage does not make sense given the power supply that we have. So this calls for some troubleshooting. And here I easily found that the battery was not properly connected, or it got disconnected when I moved the breadboard. Placing the connection back in, we can check. There is the full voltage that we get across the circuit, and the voltage that we get across the diode is around 5.1 volts, in this instance 5.08. The rest of the voltage is consumed over the resistor. And this is how you build a voltage regulator. Here are some links for further reading. Thank you, and see you in the rest of the videos.